So should I start at this point?
Yep, I think anytime now.
Okay. Welcome to the astronomy colloquium. We are traveling in a S-shaped tunnel, it turns out. This COVID tunnel is not a simple one, it's an S-shaped one. Just because you see some light doesn't mean that you're at the end of the tunnel. In fact, there's a dark spot before the final curve, and that is where we are right now, which is good news. Bad news is the last week and this week, especially here, we are scrambling around with or rather large increase in infection, fortunately, of Omicron, which is not so much the Omicron is fortunate. Fortunately, Omicron is in most cases mild. Unfortunately, we had to, because of that, we had to cancel the in-person colloquium. LA County Public Health has advised everyone to cut down on social activities, which is a pity because one of the things I had promised Jeff was after the colloquium, we would all go to the Athenaeum and in the Rathskeller and drink till the end of the evening. That he'll have to come back again. Anyway, today's speaker is Dr. Jeff Cooke of the Swinburne University of Technology, Melbourne, Australia. Jeff's area of research includes the study of high redshift supernovae, interstellar and intergalactic gas, electromagnetic counterparts to gravitational wave sources, and the study of fast transients at optical wavelengths. In preparing for this talk, I went to Jeff's site at Swinburne, but found the link to his CV broken. I guess Jeff thinks, it's no longer needed. Fortunately, I've known Jeff since he was a postdoc here, and I'd spent some time with him. So I was able to reconstruct the next few sentences from my memory. Jeff obtained his PhD at UCSD, working on damped Lyman alpha systems, and his supervisor was the late Arthur Wolf. He was a postdoctoral fellow at UC Irvine, and later moved to Caltech, where he was a postdoc with Richard Ellis, and that's when I came to know Jeff. Following Caltech, Jeff left to Swinburne and is currently a professor as well as an ARC fellow at Swinburne. As you'll see from the talk, Jeff has a very high level of energy, and his enthusiasm for research is infectious. Today, he will not only tell us about his research, but also about his next big idea, a wide-field U-band imager for the Keck telescope. Jeff, welcome to Caltech, and the floor is yours.
Thank you, Sri. I appreciate that. And thanks for reconstructing my CV. I didn't know the link was broken. And that site's about probably 15 years out of date. So, all right. Well, thanks for the invitation to the colloquium. I really appreciate it. And I realize I'm taking the place, I think, of, ASA or WS. And I was asked by different people to talk about different things. And I was wrestling with which one I should do. And so I'm going to do them all. At least I'm going to do 3 of them. So it'll be in the theme of AAS with fast talks. So at least I'll try to keep you interested in 3 different topics. They may seem quite separate: fast transients, high redshift galaxies, and an instrument, Keck Wide-Field Imager. But there's a common theme there, which I think you'll recognize right away. All right, so we'll start off with fast transients, and I'll be discussing this deeper, wider, faster program, which I've been leading for about 7 years now, I guess. It's a deep, wide, fast cadence program, as the name suggests, but it is novel in that it uses all wavelengths and particles to detect fast transients, trying to characterize the fast transient universe. So it's exploring these new regimes in time domain and this observational approach. So a slide on transients. Transients in general, I thought of, most people think of supernovae and novae, and that's indeed true. With the advent of wide-field imagers and wide format CCDs, though, that space has been filled with different populations, as shown on this chart, taken from Monsi's 2011 work, modified from that, and includes things like luminous red novae, calcium-rich transients, and even superluminous supernovae, which I work in, and I won't be talking about those today except a little bit later on. And so the wide field deep imaging, cadence imaging is necessary for these, but as more and more transients are detected, that space is being filled out. So one might ask, well, if we squish all that to the right there and look on shorter timescales, what's in this regime right here? And we do know there are things. There's gamma ray burst afterglows, core collapse supernova shock breakouts, some serendipitous detections, and some other things that are fainter than this chart shows, which are things like flare stars and X-ray binaries, et cetera. So there are some things here in the optical. This is an optical regime. But one might ask also, what else is here? And over the time the DWF program has been operating, other classes have been found, these fast luminous transients, kilonovae, and some other objects. But there still remains an area here that's unexplored on this fast time domain, and there are theorized things here are expected. So this is the area that Deep, Wider, Faster focuses on. Now this is in the optical, and another reason to probe this is because fast transients occur at other wavelengths. We know that at high energy, this is a similar scaled plot with time on the bottom and energy on the left there, y-axis, and there are many transients filling up this wavelengths or this phase space, and that's also the case in the radio with FRBs and RRATs and pulsars, etc., and GRBs. So the point here is that transients occur at all wavelengths, and fast transients do as well. And so it's trying to detect these requires all wavelength search. I'll focus on one of those transients called fast radio bursts, or FRBs, and this is an illustration of the detection of an FRB where the signal is curving through the plot here. See if I can get this to advance near that line there. And even though they're about a millisecond burst in the radio, they arrive at different times versus frequency was the dispersion measure. And so this burst occurs, but its arrival time is later at the longer wavelength you go. So because this is the radio, if you want to detect a counterpart to a fast radio burst, say in any other wavelength, that's a shorter wavelength, if it's a coherent burst, that's actually going to arrive to Earth before the radio detection. So any reaction or triggered response is going to be too late, if that's the case. And so you need to actually be there before, during, and after. So that's just an important point I want to make right up. So fast transients in general, we're talking about millisecond to hours duration transients, up to maybe a day or two. And they occur in one, multiple, or all wavelengths. Some of the wavelengths are unknown, some theorized events. They include, of course, high energy, particles, gravitational waves, and some emission arise before their detection, as I just described with FRBs. These are rare, so you need wide fields, and you have to act fast. Since they're so fast, you need fast exposures, short exposures, fast cadence. A short exposure is necessarily shallow, so you're going to have large telescopes to get the depth needed. And so you need deep, wide field, and fast. Also, because these are rare, and many of these wavelengths are unknown, or it appears in multiple wavelengths, the idea is to do just simultaneously get all wavelengths on a field at the same time to get all possible information before they fade away. If for the things last a little bit longer, maybe last a half an hour or an hour, if you can process those data in real time, you can then be fast enough to trigger on them and get a spectrum and understand them in more detail. So you need fast, rapid response spectroscopy and imaging. All of this needs to be done very fast, just moments after the light hits the telescope, and the Deep, Wider, Faster program does this. So in short, it's essentially 4 steps. We have this coordinated simultaneous observations, where we coordinate 10 of the world's best wide field telescopes at all different wavelengths, including particle detectors, and when gravitational waves are on, of course, that's extra information. We focus them at the same fields, a couple hours at a time over 6 nights, and that usually happens about twice a year. And these are deep. In the optical shown here, optical is deep. They're about 23rd magnitude, plus or minus, for a 20-second exposure continuous. Then we do real-time data processing. The radio detections, like FRBs, are detected in real time. High energy is detected in real time by the satellites. And the optical data are processed through our Swinburne supercomputing processing, and we have this lossy data compression to speed up the process, et cetera, which I can talk about more later if people are interested. But in short, the processing just happens in a few minutes and continuously through the night, and we look for transients to respond to. And so we coordinate with proposed and collaborating facilities to do rapid, minutes later or hours later spectroscopy and imaging with ground and space-based telescopes. And then finally, we have some longer-term cadence imaging of those wide fields, because for example, for some fast transients are associated with slower evolving events like supernova shock breakout. For example, if you detect one, you want to know what supernova that's associated with, etc. So let's see if I can get this to advance. There we go. So in 2014, this program started. So in January 2015, we had our first observations, and we coordinated the dark energy camera and the optical, Parks and Longwell and the radio, 2 different radio frequencies, and then Swift doing gamma ray and then UV and X-ray. And it was successful observations. And then by the next year, we added the program grew with some follow-up telescopes and other observing telescopes. And this is when the gravitational wave detectors came online. And now we've grown to gigantic proportions for over 80 different facilities. Now, keep in mind that only 30 or so of these are used at any one time because you're working in a hemisphere, but it's a very large undertaking. And we detect all kinds of fast transients and known things like flare stars and auroral Lyrae and cataclysmic variables, et cetera, and some really weird things that we've been studying, that like this one off to the right here, which had a little burst and then 3 bursts and is gone forever. So there's some unusual things that we're finding. Because it's a 6-day consecutive program, we see things like novae. And so here's an example of a nova detected in a nearby galaxy. And we're actually placing good constraints on the nova rate, which was surprisingly not as well constrained as I thought. Kilinovae, because we were going and operating in multi-wavelength fashion prior to GW0817, we were ready. And so when that event happened, we got 15 facilities online and did some quite good observations, detecting it with SkyMapper spectra, including one of the first spectra with 2.3 meter and IFU spectroscopy, et cetera. So we covered that well. And supernovae, which are slow evolving events, but we try to catch them early because early data is very important. And of course, supernova shock breakouts, et cetera. I won't talk about any of those, but I can, if you'd like to know. I'll just finish up this section with our September 21 and some interesting results from that. So in September 2020, go back to that time before COVID-19. And so we had dark energy camera as our main optical imager, but that was closed due to COVID. So but KMT-net stepped in. It's a 1.6 meter wide field imager at Siding Spring. But we coordinate these facilities here, Swift, HXMT, Astrosat, Parks, Malonga, and Huntsman, as well as KMT-net, to observe simultaneously. We detected 2 high signal noise FRBs and 2 low signal noise FRBs, which is quite remarkable because FRBs take a long time on sky typically. We pointed at this field FRB 190711, which is a known FRB repeater, just to look for a repeat. And as a note, we didn't see a repeat, but we did see these 2 other FRBs here. And they're rather close on the sky, which is interesting. The DMs for them are pretty similar, which is also kind of interesting, especially for the 0919 and 0711. Kind of, it's possible that they could be maybe even at the same large cluster or something, which is also interesting. Here are some of the facilities we had online during those 2 events simultaneously, and you can see their names on the left here: HXMT, Swift, Astrosat, etc. High energy, optical, and radio. The event happens where you see this vertical line. And this first one happened at literally the last minute of the run, which is how things happen, right? And then the second one was actually when we came back on sky a bit with the radio telescopes. Just to summarize this quickly, most facilities showed just an upper limit on a detection at another wavelength than radio. The optical is at the top here with KMT-net. It actually stopped observing at the time of the FRB, but got up to about 2 minutes before. And we see some event here that this is a light curve, and there's just a little hump here. If you can see my curve here, a few sigma detection in a source, which we're looking into, but is a possible candidate. And then below here is some upper limits from the different X-ray telescopes and UV instruments. And that's all in a work postdoc of mine. We did some follow-up of the higher signals noise event, which is this 2009-19, and this just shows you after the fact coverage. So we have different optical, high energy, and radio telescopes looking for a repeat to see if we can localize it, plus also looking for any kind of other burst. No repeat was observed. But the last thing I want to comment up here is one of the low signal to noise detection FRBs, because this one happened in the same beam as the high signals noise one that I just mentioned a minute ago, but at a lower DM, something that would put it at redshift about 0.1. And we search, for all our FRBs, we search over all time because any FRB could be associated with a burst maybe years before or after. And we saw that there was a detection on about 14 months earlier. And this just shows you kind of the sky coverage. So this is, the blue is the beam for the high signal to noise detection, black for the lower signal noise, and this little circle in the middle here is the galaxy of interest where a transient was discovered. That transient was discovered by Master. In this transient, we got a spectrum of that host galaxy, and it was 0.79, which puts the transient at minus 20.8, which would be a superluminous supernova. Now that's a bit interesting because superluminous supernovae are very rare, and so are FRBs, and to have them in the same area is just interesting. And this just shows you that it was off center, so it's unlikely to be an AGN. So that's food for thought. We're looking into that further, but that's an interesting result there. And I'm going to shift gears to the next part. This is going to be high redshift galaxies. So let's get your brain onto high redshift galaxies. And the aim, or the point here, is that broadband imaging can do some remarkable things that people don't typically think of. That is also understanding spectroscopic and kinematic properties of galaxies. And I'll explain that in a minute. So the galaxies I'm looking at are Lyman break galaxies. So shown on the left here are two far ultraviolet spectra of Lyman break galaxies. The blue has Lyman alpha emission, which is this feature right here, if you can see my cursor, and the red has Lyman alpha absorption. So in shorthand, it's ALBG for an absorbing, Lyman alpha absorbing LBG, and ELBG for an emitting. So these are two quartiles of the LBG population. And if you plot them on a color magnitude diagram as shown on the right, you can see that they actually segregate in space. And that's because if you look at, here are the two filters, G and R band, which are used. The G band probes the Lyman alpha feature in this break here. And the R band probes the rest band UV continuum, but you can see that there's a difference here. These are normalized around 1300 angstroms. And so this difference in the R band and the opposite contribution to the Lyman alpha feature causes these to segregate in space. And so if you have these two populations which have a distribution, that green line is separating those two distributions. And if you go about 2 sigma away, which are those dotted and dashed lines, you actually can get two regions which are quite pure populations. Yuping, I'll answer your question here in a minute. Sorry. Okay, so you get these, if you look at these red and blue regions, you get these two rather pure, or they can be actually pure if you go further and further out, depending on the numbers that you have, regions using broadband imaging to determine if you have an absorber or an emitter. You know, why is that interesting? Other than you can do that is because Lyman alpha has been associated with a lot of other properties. If you look at this, these images over here, the absorbers are morphologically different. They're larger, more diffuse, multiple star-forming regions. The emitters are compact and single star-forming regions, and that's just 2 in this other plot over here. And there's also a lot of properties like their UV continuum slope, which is what's helping to separate them on the CMD, but that can speak to dust and age. The ISM absorption line strengths. Here we're seeing the different quartiles absorbing to emitting, how their properties change. So there's a relationship in each one of these. And outflows also show a relationship. And all this work was done by Alice Shapley back in 2003 and David Law in 2012. And so there are a lot of properties that are associated with Lyman alpha. And if you're going to isolate those, you're actually isolating galaxies with those properties, because these are remarkably consistent in that context. And I have a student working on this where that has worked looking at the kinematics. So something you would not think you could do with broadband imaging, but using these color magnitude diagram again, which does segregate these by Lyman alpha, shows that here is a color magnitude on the left of redshift 3 galaxies. And the red objects here are the ALBGs, Lyman alpha absorption, and the blue are ELBGs. And things that are circles are rotators, and diamonds are dispersion dominated. And this is at redshift 3, and this is at redshift 2. And the takeaway here is, if you remember these like separation lines I showed you, like these dotted and dashed lines you can barely see in gray here, there are these regions up here where the absorbers are the ones that are confirmed are solid, are rotators, and the emitters down here are dispersion dominated. And over here at redshift 2, where there's more data, it shows up more, where you see all the rotators are absorbers, and there's a dearth of emitters, but those are dispersion dominated. Mergers are stars in this plot. So it's very interesting, and there's a program to develop that further. But shown here is basically a plot of the net Lyman alpha with equivalent width, so absorption down here and emission to the right. And this is a proxy for rotation. So a rotation would be high on this list, and dispersion dominated would be low on this y-axis. And so this dashed line here, these are dispersion dominated and these are rotators. And what you can see from that plot is that rotators are, it also shows you the color on the CMD, red to blue. So the redder objects that have absorption are rotators, and the bluer objects with emission are dispersion dominated. And that absorption isn't due to orientation, because you have a number of these, which is shown in the table in that work, that are analyzed, and there's no dependence on orientation. So it's not something that's intrinsic to the galaxy. It must be farther outside or some other scenario. The last thing I want to talk about on this section is correlation functions. So most people probably aren't very good with these, so I want to give you a 101 really quick. So this is on the right hand, we have just some arbitrary dispersion of galaxies on the sky where they're concentrated at one point. So they're clustered. And if you were to take all the separations and measure them, this correlation function here is measuring how many of each bin separation bin. So we have small separations to the left here, and then larger separations. So this is compared to random. So you have an excess of objects with small separations when you're clustered, because there's a lot of small separations here. And this shows you there's an excess here with smaller separations. So this is just what a correlation function looks like when you measure all those separations. If you lay another population, same kind of population, randomly generated on top of that, you get another green correlation here. So these are autocorrelation functions. But importantly, if you do a cross correlation, so you're measuring green to red separations and red to green separations, you get a cross correlation function. In this case, it's also the same because they're just on top of each other. But the reason that that's important here is that if you do that same correlation function, but you move your other populations spatially somewhere different on the sky, you see that their autocorrelation functions are the same, but the cross correlation function shows an anti-correlation. So that signature shows you that these aren't in the same places in the sky. So that's going to come up in a minute. And this just shows you that if you have a weakly clustered population in blue, its correlation function looks like this. This is a 2 halo component. Strongly clustered in green, it's higher here, stronger. And if you have them really tightly clustered, like a 1 halo component, you see this black here shows like a peak right here. So correlation functions for galaxies look basically like a 1 halo component here and a 2 halo component. Okay, so this is a correlation function for LBGs. The black is for the full population. There's the 1 halo component and the 2 halo. And the red is shown here. And so we took a whole bunch of galaxies, segregated them using this method with photometry, and plotted them onto the correlation function, and made a correlation function. And what this shows is that the one halo term for LBGs is, these are just drawn on here, so they're not accurate, but is around 10 to the 12 dark matter mass. But the absorbing, or ALBGs, look like they're in much larger halos, something that's like grouper cluster size. That's what this is indicating. And it's also shown by the 2 halo term being higher than the galaxies, the population as a whole. And with LBGs, they look similar to LBGs, but they have this funky two halo term, which I'll come to in a minute. And this is their cross correlation. So what I want to show you is that the two do not exist in the same place. There's an anti-correlation, especially at small scales. And so that's interesting to show that these galaxies are in different physical locations. This looking at this odd behavior of the emitters, we take a look at a normal clustered population here. This is a normal correlation function. But if we were to decide to put galaxies in shells, shown here with nothing in the middle, you would have a correlation function like this lavender one. Now, if you do different combinations of that, 100% shell, 80% shell, mixing it with a regular cluster population, you get these different correlation functions here. And the LBG correlation function looks to follow the 50 or 60% shell function very well, including these dips, which do not go away in the theory, or in using the modeling. Bottom line there is that absorbers are in massive halos, groups and cluster environments. Emitters are not, they're low mass halos out in the filaments in the field. And in fact, avoid groups and clusters with some characteristic radius of a few megaparsecs. And lastly, using these functions, we see that the absorber function is, the red dots here are above the whole population of black. The blue data is above the black. And this right here is the in-between, the ones that have combinations of emission absorption, and they're similar to the black. So nothing is below. And what that means is that by combining all by looking at a high redshift galaxy population as just a single population, it's like looking at low redshift galaxies, ellipticals and spirals as a single population. And you're misidentifying and using regular correlation functions to measure the mass, you're actually underestimating the mass. And also, it just suggests that we should really be looking at high redshift populations as distinct populations, two populations. And lastly, I'll talk about this WhiteField Imager. And so the common theme here is that WhiteField imaging, broadband imaging, is able to do this work. And it's progressing these areas dramatically. And so partnership between Australia and the US is looking into building this instrument, and it's progressed quite far. So in Australia, there's Swinburne, ANU, and Macquarie universities, along with the AO, and University of California and Caltech and Keck are involved here. So this for the next few decades, this is going to be the most powerful imager on Earth or space, actually for the foreseeable future. And then there's a large gap in imaging, wide field imaging, as you'll see, that we're facing right now. And this imager can do science that cannot be done on any other telescope, not even 30-meter class telescopes. So it's going to help Keck remain a leader. Wide-field imagers are fundamental to astronomy, nearly all research areas, and this includes other wavelengths, as you heard from earlier in the talk. Radio detections, high energy detections of transients, for example, not always well localized, and you need a wide-field optical imager to find the source, to get the host galaxy, etc. These are the highest demand instruments on their respective telescopes, so it's just a testament to their need and their value. So that way, KWFI is going to be a facility instrument doing discovery, surveys, and science, and again, unique science. So if we look at our landscape now, we've got some instruments that are being proposed or coming online, like Keck Phobos, which is a wide field fiber spectrograph, Mauna Kea Spectroscopic Explorer, also wide field spectrograph, and Subaru prime focus spectrograph. There are these mega facilities, which are the square kilometer array radio facility, which there are pathfinders now, ASCAP, MeerKAT, and MW are already operating. The Trancop telescope array for high energy, along with a bunch of other high energy and particle detectors that are all sky and wide field. Then there's the very sensitive telescopes like TMT, 30-meter telescopes, and James Webb. Current gravitational wave detectors, which are detecting events farther than we can reach currently, and even next generation gravitational wave detectors, which will go farther. And then there's even the Roman and Euclid wide field infrared space telescopes that'll be launched. So there's a lot of telescopes coming now into the future. And if we look even 10 years past and then 10 years in the future, at all wavelengths, all other wavelengths, wide field is the dominant mode for instrumentation. And so we need to keep up with that in the optical. What exists currently? Well, there's CFHT Megacam, CTO Dark Energy Camera, and Subaru Hypers Prime Cam with the Rubin Observatory coming online soon. Now, the CFHT Megacam is going to be end its life and make way for the Mauna Kea Spectroscopic Explorer, which I just mentioned. So I've shown here just the Dark Energy Camera, Subaru, and Rubin, which will be the telescopes that will exist. Now, Dark Energy Camera is a 4-meter telescope. It's good. It doesn't get quite as deep as the others, and it has poor U-band sensitivity, which will make a difference in a minute. I'll show you. Hypers Prime Cam is great. It's the premier instrument there is. It has limited access, and it's going to be even more limited as its optics will be used for prime focus spectrograph, but it'll still have some use. But it has no U-band, which is important, and it has things like 30-minute filter changes, which make following up transients such as like kilonovae essentially impossible. And then there's the Rubin Observatory, which also is going to be a very good telescope and survey, but it's a survey of the sky, right? It has, for the first 10 years, it'll be doing its LSST. You're not going to be able to just propose for Rubin to do your science. And the transient program and TRO programs are yet to be understood, or if there'll be anything. So it has some limitations, as you'll see. When it comes to transients in gravitational wave science, all we'll have is DECAM for the future. That's it, for decades. And that's good, but that's a problem. And so the idea is to have Keck Wide-Field Imager come into here. So it has not only the larger aperture than any of these, so much more sensitive, as you'll see, and it has U-band throughput and superb U-band throughput, so it can do a lot of science that none of these can do. But it does cover all of the northern and 2/3 of the southern sky, and will have TOO capability to get things like gravitational waves and transients of all wavelengths. The Keck telescope was designed to have a prime focus camera. This is the upper cage, the prime focus cage up here. And what you do is you can just point Keck down to the horizon there, and you have these modules inside that pull out, and roll in, these little modules. And so you can just install KWFI, and that takes about 2 hours. You can do that in the afternoon. But one thing we want to try to do is to actually have it installed permanently, as you'll see in a minute, with a deployable secondary mirror. But if you look at the Keck Blue Book back in the day, written in the 80s, I guess, or when it was written, they show there's the prime focus spectrograph in there, and you can have a look at that. But back then, it was too difficult to tile such a wide field. CCDs were new and expensive, and I think they were even thinking of photographic plates. But now this is possible. And so this is a picture of the camera in the prime focus cage here. The cross section here shows that it's a very simple instrument. A couple of things I want to point out is that it just has 4 optics, 4 lenses, which is half of what Hyperstream Cam has, and so increases the throughput dramatically. Has this novel ADC, which I can talk to people about if they're interested. It has a filter exchanger and shutter that are the same design. We actually got approved to use the design on the Dark Energy camera, and if anyone's used that, it's amazing. It has 15 or 10 second, about 10-second filter exchange, which is much better than 30 minutes, guaranteed. And it's very reliable. It's been on for a decade almost and doing fantastic. And the shutter is fast too. It has a 1/10 of a second accuracy, and this is a 2-meter shutter, so that's quite remarkable. And then there's the detector here, which is based on the heritage of the ZTF, which is just fantastic. So it has all of its R&D already done. And so this shows you the instrument from the side, and there's on the left there's a secondary mirror that could be in place when you're running all the other instruments if this thing's permanently mounted. And then you can just flip it out of the way to get to image with KWFI. So you can imagine imaging, and then our data reduction pipeline with this will process things within just a few minutes. And then you can find your objects of interest and configure spectroscopy, and you can just, oops, sorry, wrong way. You can just flip down the mirror and you get spectroscopy right away. So that's an extra capability to enable new science. The altitude of Mauna Kea provides very good UV throughput. So it's going to be able to, so KWFI will do unique blue science. This is a 5-filter broadband filters, Sloan filters, UGRAZ. It's just their convolved throughput with the atmosphere, which is the solid line, the quantum efficiency of the detector, which is the dashed line, and the optics, which is the dotted line. This is just, so the throughput shows that it's very good blue, including U-band, and then still quite good in the red, but it drops off in the far red. But that's the current design. So if you have science that requires red, let me know. But if we look at Hyperspace Prime Chem comparatively, there's a lot here, but the gray, light gray curves are what would be the same plot for Hyperspace Prime Chem on this plot here. There's no U-band for Hyperspace Prime Chem, and its throughput is worse because just for different reasons. It's got more optics, etc. But this dark gray band down here, which is the same thing but lower, that would be if you were to compare them flux per second. So if you got on the sky and you pointed one and you pointed the other and just started getting data, how much flux per second comparison? As you can see, like in the I band, KWFI would be about twice as much, G band maybe 3 times as much, and then of course infinitely in U band and about the same in Z. And this is just what scaled Rubin would be on that same plot. Here are some numbers. It's sensitivity numbers. So I don't know what your science needs, but it's very fast. As you can see, with just 5 minutes, you can go deep. And with a dedicated program, you can get to 29/30th magnitude, which is new territory and new ground to do some exciting science. It's very U-band sensitive, as Sri mentioned at the start. Fast readout, it's about a 10-15 second readout. And this filter can be exchanged within that readout time and has this multiplexing capability. Oh, at the bottom is just a comparison of the Hyperspace Prime Chem deep survey. There's 2 pointings. They did a very deep survey. We spent a lot of time on it. As you can see, those depths can be achieved by KWFI pretty quick. And just comparison with the LSST survey, in this left column here with the teal underscores, that's the depths of their stacked 10-year, take 10 years of the data and stack it. That's the depths they'll reach. And so, they'll reach to 27.5 or so and 26 some change, 26.1 in U-band. And this is in the right-hand column there, this is how long it would take KWFI to get those depths. So although LSST is a wonderful all-sky survey, for targeted science, KWFI is very much faster and can do the science better. This is the footprint of the field of view. It's the kind of a Swiss cross design. There's a 6K by 6K CCDs. It minimizes the chip gaps and technology, increased technology. Then we have CMOS detectors in the corner that does focus on guiding, but can be used for science. So if you have science that needs like millisecond or fast science exposures, that's capability. And again, this is all based on the ZTF heritage. So we're very fortunate to have that. As you can see, there's comparison of other instruments at Keck and their fields of view. And the field of view then compared to things that are going up in space. So there's Roman Space Telescope, field of view in yellow, and Euclid here. These are the wide-field infrared space telescopes that are be launched. This is Keck LRIS, so it's going to be able to tile you'd have to tile quite a bit just to get one pointing. So the Keck Wide-Field Imager, as you can see, is well designed for this type of field, so you can cover it in U-band, which is necessary. And then this is the Mauna Kea Spectroscopic Explorer footprint. So there'll be 3,000 or 4,000 fibers in there, so you'll need a high density of faint targets. And this is a Keck Phobos field of view here. So the space telescopes kind of cover 5,500 angstroms onward to 2.5 microns, and there will be some UV satellite proposed that'll cover 2,800 and down. But this key range here in between is missing that KWFI will fill between 3,000 and 5,000 angstroms in particular, because for most of the science being done by these space telescopes, you need photometric redshifts, you need a high redshift galaxies, you do dropout, and for weak lensing, et cetera, requires really deep 29th magnitude, even 30th magnitude in these wavelengths, 3,000 to 5,000. There's no other instrument or telescope facility in the world that can do that, except KWFI. Tons of science you can do, can't get into any of that, but it ranges everything from solar system to stellar populations and local galaxies to transients, time domain, to lens galaxies, to reionization, right? It's all over the map. So it's not a niche instrument, it's a full-on facility instrument. I will mention quickly, I think I have a couple minutes here. Yeah, it's only 4:40. That one of these are two of the highlight science cases, I guess you could say. So one is reionization. Galaxies that reionize the universe emit Lyman continuum flux, and that's short wave 912. And to do it from the ground, You can only do this, well, firstly, you can only do it from redshift 3 to 5. Beyond that, the universe is too opaque. And redshift 3 to 5 galaxies, that short word of 912 flux falls in the U band. That's it. So you only can do this with deep wide field U band. So KWFI would be the only instrument that can detect this flux, map out ionizing sources that go up to, reaching up to the epoch of reionization. You connect those, you look at those galaxies, find properties that connect to their Lyman continuum, and then you can extend that on the way through reionization. This is also the redshift range, which the square kilometer array is going to be mapping neutral hydrogen. So now you have a beautiful marriage of ionized sources mapped and neutral hydrogen. You can understand reionization very well. And KWFI can detect supernovae from redshifts 2 to 7 and understand their far ultraviolet properties, because at redshifts higher than that, superluminous supernovae can be detected at redshift 20, but you only see their far ultraviolet. Even with JWST, you're only looking at their far ultraviolet. So KWFI will characterize their far ultraviolet, and then you can detect them all the way to redshift 20. So all this epoch of reionization, high redshift universe will just be dominated by KWFI. And lastly, the gravitational wave detections. So for the far future, now for decades, any telescope larger than 1.8 meters to follow up wide field imaging is here. DECAM, shown here, at DECAM, and then potentially Rubin at some point. And this is their area of reach in that green. And so the northern hemisphere is missing, essentially. And KWFI with this location will cover that, including 2/3 of the southern sky. This plot shows how effective it really will be. 1 meter class telescopes can reach out to about 200 megaparsecs per kilonovae. DECAM, which will be our only instrument available, can reach out to, shown here, maybe as far as 500 megaparsecs. But the rest of that is already, the detectors are reaching farther than that, and the advanced detectors will reach farther. KWFI can reach all the way up, so that it'll be able to detect 90-95% of the kilonovae that will be missed. So I'll just mention that there's been a lot of work to date. Detectors being developed here at Caltech. UCO is doing a lot of the mechanical work with the body and lens mounting and electronics. And and Australia, they're doing the optics design, filter exchange mechanism already being built, and a lot of work on the data reduction pipeline, the instrument control, and also the user interface is being done at Swinburne with the ADAX facility, which is a data and computing services. So that's KWFI, and I worked you through 3 completely separate things. So thanks for your patience. But the simplified timeline here is that we started working on this in earnest in 2019. It's been well supported by Keck and SSC, so we thank you very much for the support so far to get through the conceptual design and proposal readiness reviews, et cetera. And now we're proposing for some major funding. And if that comes through, there will be construction coming up in 2023, and it could potentially be finished in 2026 if all goes perfectly, but nothing does. So we're going to say about 2027 that this could be on sky. This is just a movie, oops, I'll leave you with, which is a 3D printed model that the Swinburne Factory of the Future made of KWFI. So it's interesting for illustrative purposes and design purposes. I'll try to turn down the sound a little bit. Yeah, so let me get that going again. So this is a 3D printed model, and it's actually quite large. It's a 1/4 scale, so you can see with a person here. That lens there in front is actually a little over a meter in reality. And this shows it in the cage, and it fits well, and you actually have room for that deployable secondary that I mentioned. And installs quickly. This back, it rotates because it has to rotate on the sky. Text and Alt-Az telescope. If you take off that detector, that red thing in the back, you can see through it. And the Swinburne Factory of the Future is building this filter exchange mechanism. So this video demonstrates that, how the filters move in and out pneumatically. And so it's quite a simple yet powerful instrument, and it's a capability that Keck really needs. And actually, as I mentioned, it can do science that just can't be done anywhere. So keep Keck the leader. But this is it from the side, at least as it was. The design was a while back. And thank you for your time. Appreciate it.
Okay, thanks very much. Well, since you're such an advanced project, such an advanced stage with a 1/4 scale, but it's almost there.
That's right.
Okay. That sort of reminds me of this thing called the Russian stone soup theory, which I'll explain to you over drinks, Jeff, later, how it works.
Okay.
Okay. Questions?
Yeah, I think there was one in the chat. What was the delay between the superluminous supernova and the FRB? It was 14 months. So, if they're associated, it's a very big if, right? Yeah, that helps. Yeah.
Okay. Please raise your hands if you have a question. And once that question is answered, then lower your hand. And if you're wondering where the hand is, go to the bottom of your screen. There's a little knob which says reactions. I think usually it's fun. Yeah, there's a raise hand.
Yeah.
Okay, Ranga.
Hey, Jeff.
How's it going?
I was about the Lyman alpha emitters versus absorbers, the absorbers being, relatively rotation-dominated large things. I mean, that's not really surprising, right? I mean, you're in Lyman alpha emitters, you're picking up the brightest compact star-forming galaxies. And as those evolve with time, you have outflows and the galaxy builds up mass. And just because to get the Lyman alpha absorbers, you need to have a high cross-section, and the highest cross-section is the large fluffy things, which aren't necessarily you're not going to have a starburst on a 10, 20 kiloparsec scale unless it's an SMG. So just in terms of number densities, it seems to me that it's almost intuitive that the absorbers would have to be large, fluffy, rotation-dominated things. So you seemed surprised by that. And why was that?
I'm not particularly surprised, but one thing that was there's several things here. One is because there was no orientation dependence, it doesn't seem that it's just because it's a larger thing that larger thing is causing absorption, right? Like they have star-forming regions, and then you've got a big disk that's absorbing it. Well, if you would see that face-on or something, you would think maybe that's not the case. But the face-on ones actually were more absorbing or equally absorbing to edge-on, which was just interesting. But aside from that, I do agree that absorbers, more massive, rotating, okay. But that's, on one hand, it's very powerful that you can find these things just with broadband imaging, right? You don't need narrowband, you don't need spectroscopy, you don't need IFUs. You just say, I have a certain color in broadband, and that's going to be a rotating absorbing galaxy. That's kind of cool, right? And so you can do this, and then you can start doing this on very large scales, thousands of megaparsecs over millions and billions of galaxies. And then it becomes something where you add this extra component of kinematics if you want to like halo match simulations, for example, right? Not only do you just say, oh, we got a mass by a correlation function, we match it. Now you can say, oh, well, actually these particular ones have rotation, these don't. So it starts becoming much more powerful, and you're just using broadband imaging, which is kind of crazy, right? So, I mean, I think that's what a lot of this is going, yeah.
Got it. Okay, thank you.
Sure.
Other questions? Mansi.
Hey, Jeff.
Hey.
I wanted to ask you about your quest for optical counterparts to FRBs. For that first one that you showed some sort of a blip, but what was that amplitude?
Yeah.
And do you actually believe it? Is there something exciting there?
Yeah, so this is try to find it. This is work that Jilai Zhang, my postdoc, is doing, and let me try to lost you. Sorry. Put this back up. Yeah, this blip is a blip. So it's a source that we have yet to confirm whether it's a galaxy or not because it's of its faintness. And we just got to get it, we'd have to like sit on it with Keck or something, but it's a over 3 sigma for, I don't know, 3 or 4 data points here. And each one of these data points is a minute or 2 minutes because of the minute readout. And so
but there's no counterpart in legacy survey or to deep limits right now. It's hostless to whatever deepest images you have at the location. To whatever deepest images you have at that location, there's no host, no star, no galaxy.
There's a host. There's a host.
Okay.
Yeah, so this is a host that's brightening, like something in a host. Can't be 100% sure that it's a galaxy. So if it's a star, then obviously it's out, right? So, or it doesn't obviously, but it should be obviously, right? And so, so it's just it's one of the detections that she found. It also precedes the FRB perhaps too much. It's like 4 minutes before the FRB. It's a bit suspicious, right? And so it's just it's a possible candidate. It's nothing that I'm going to, jump up and down and say exactly.
Okay. And your superluminous supernova, you're not too excited, is what I gather.
Well, the weird thing about this is, firstly, okay, they're both in the same area of the sky, and so you got things like the FRB that it's associated with is low signal noise. It's signal noise 9. Now 9 sounds great to us, but when you do FRB work, it's 10 or higher is usually the cutoff. And so it's lower signal noise. So they look at that and they're kind of like, yeah, I think it looks like an FRB, but there's some question, right? So you have that already on the FRB end, right? And then you say, okay, when there's and that error region is about the size of that circle. So, it may not be that galaxy in the middle, right? I mean, it's close to the middle, but right? So you have that, you got to figure out the probability of that. But the fact that it's super luminous is quite interesting because you just don't see those that often, right? And to have it right there in the beam.
And is the DM consistent with the redshift or not?
It is. So the DM of the low, I know that's what makes you go, right? Because the DM is like I think it was like 100 or something, 110, and with that model it puts it at about 0.1. No, maybe it was low, whatever it was. It puts it close to redshift of 0.1, and this event was 0.8 or 0.08 or something, right? Whatever. So you can see it's 0.079. So I mean, sure, it's consistent, right? So it's so it's all those things coming together where you say, well, maybe, right? It's a star-forming galaxy, could host a superluminous supernova. It doesn't look that. It's one of these, it's got star-forming, but it's not booming, right? It's got calcium lines and stuff. So it's a little bit older, but yeah. Just interesting.
Thank you.
Yeah, sure.
Liam?
Yeah, so just staying on this FRB for a second.
Yeah.
The other two FRBs that live in a galaxy that host things like superluminous supernovae are highly active repeaters with persistent radio sources. So has there been much follow-up on this subthreshold one?
There was a lot of coverage of this field previously by ASCAP, which hadn't seen a repeat of 190711 or anything there. I probably would have reported anything. However, they're also always looking for signal noise 10 and above. So if this is always weak for some reason, then they're not going to see it. Since then, there's been maybe only one time that this has been covered by ASCAP. Yeah, since then. But we intend to hit this next year with Parks and ASCAP as well. So we'll see then. Yeah.
Thanks.
Yep.
Pradeep, go ahead.
Hi, Jeff. It was a great talk. So I wanted to ask, what is the shortest exposure time on the optical readouts? Maybe I missed that. And the second part of my question is there any plan of incorporating MKIDs for fastest readouts on these on the, well, not necessarily for the wide field, but just for the fast readouts?
Yeah, so with DECAM, because we need wide field optical for the purpose we're doing, those are 20-second exposures with about a 20-second readout. It's a little longer actually, but is intended to be 20 on, 20 off, but it ends up being about 25 off. So the 20-second exposure is continuous. When we use Hypers Prime Cam, they're 30-second. And with this particular run where we used CamTNet because DecCam was closed for COVID, these were minute exposures, consecutive. So that's the exposure times. I definitely would love to go to something faster and, something that has no readout or, essentially no readout. And for this work, wide field, unfortunately, is necessary, and ideally you'd want as wide as possible, many square degrees, which is asking for the moon. But if you have like a repeater, for example, where it is, sure, then you can sit on it and do that work. So one of the things, say with KWFI, since it is wide field, you could do a wide field search. But if you stick a known repeater in one of those CMOS chips, for example, you could be monitoring that, very fast with 10 meters behind you, because any optical counterpart should be quite faint. And then you still are doing this wide field search, right? You can have radio or something. So that's one idea that we could use that for, if that's answering your question.
Great, thanks.
Sure.
Questions? Okay, Jim?
Yeah.
Yeah, so I had a readout question too. What is the planned readout time for KWFI?
I think it's about, I get different numbers, but it's between 10 and 15 seconds. So there's the STA chips, and you can probably read up online what they are currently, and that could evolve with time. But it's definitely less than 15 seconds, and it's closer to 10-second readout. And the aim is to keep that similar or the same as the filter exchange, so you can just be changing that out at the same while you're reading out.
Okay, great. Yeah, shorter readouts mean you can go for shorter time scale variability, which is always helpful.
Absolutely. Absolutely. And it's just more time on sky, right? Who wants to sit with a readout, right? Yeah.
Okay, other questions? So I had one question, and we can close with that. I didn't realize, what made you choose STA versus other, the more usual choice?
Roger Smith would have better details, but STA is just a choice, but I think it was a combination of cost per pixel, performance, and actual availability, because there's a lot of dynamics going on in this detector world these days, and facilities are moving and merging and stuff. So I think it's a bit volatile, and I think this was more of a stable solution.
I see.
Yeah.
Yeah, that could be because E2V was bought up, I think, by Teledyne. So,
right, that's right.
So we got really a good deal with E2V.
Yeah.
Yeah.
It's like Mike Lesser kind of backflip. Yeah.
Okay. So thanks very much. And good luck with pursuing funding for the Keck KWFI. Okay.
Yeah, the name, another K.
Yeah, you have to come up with a better name. It's good you already done the 3D printing, but
no, that's okay. It's the thought is it's wide open for a donor name, right? You get like the Bezos cam or something, right?
Okay, well that's oh well. Okay, so let's take leave. Goodbye, everyone.
Thank you. Thanks, Sri. Thanks, everyone.
Thank you, Jeff.
Yep.